Everybody could. All right. So anyway, so the reason that mathematically pure water is 56 molar is the definition of molarity. Brett, do you have an answer?
No, I was just having a question.
Okay, question.
Is an arachnid a bug?
An arachnid is a bug?
Is it? I'm saying no, not saying yes.
Oh yeah, definitely a bug. Yeah, anything that offends you with the number of legs it has is a bug.
Okay.
So like, so things are supposed to have 2 or 4 legs, like 4 limbs. So you're like kitties, 4 limbs, cute. Koala bear, 4 limbs, cute. Bug, 6 limbs, not cute.
So that means a centipede's like 4 bugs?
A centipede's like 25 bugs.
Oh, okay.
Yeah, or no, 16, what's 100 divided by 6, that's 30 something bugs. Yeah, so, yeah. A bug is anything that offends you with the number of limbs it has.
So that means a spider's 1 in...
12 bugs. Yes, a spider is 12. A spider is a bug. Yes, a bug.
It's a bug, it's like 1/3.
It's a bug and a half. Yeah, or a bug and a third. But it's a bug. So anything that would be like, ooh, there's way too many legs on that, that's a bug.
Wait.
Yeah.
What if someone lost like a limb and you're offended by it? Does that mean someone can be a bug?
No, you can have 4, 3, or 2. But if somebody grew an extra limb, that would be gross. That would make it a bug.
So is your head a limb?
No.
But it's an extremity.
That's okay. But we were talking about articulating limbs that you can use to pick up and walk on things. Kitten, 4, okay.
How many legs do ants have? 6.
6.
Okay, so they're outdoor.
Bug, yeah. All right, so back to this, 56 molar. Again, it has to do with what we define molarity as. And molarity is mole over liter. Make sense? So basically the idea is how many moles of water do you have in 1 liter of water? So 1 liter of water is 1 kilogram of H2O, important density, which is 1,000 grams of H2O. Now, exactly, so now divide, so we realize that we have 1,000 grams of H2O, and we can do a simple one-step stoichiometry and realize that there are 18 grams of H2O in 1 mole of H2O, and that will tell us, I think it's actually like 55.6 or 55.7. Alexa,
It's 55.5.
what is 1,000 divided by 18?
55.5.
1,000 divided by 18 is 55.5556.
All right, so anyway, so that's moles.
So it's 55.
55.
Yeah, it's 55.5.
Like I said, 50, that's a lot of 5s. 55.56 moles, and that's in 1 liter. So technically, there's 55.56 moles in 1 liter of water. So using the definition of molarity, there's the molarity of pure water is 55.6 molar.
Huh.
Cute, right?
You know.
Useless, but cute. All right, so let's go back to talking about strong and weak bases. So I told you that there are 6 strong acids, and there are. According to the College Board, there are only 6. The halogens starting at chlorine and ignoring acetine. So hydrochloric, hydrobromic, hydroiodic are strong. And then the big ones, sulfuric, H2SO4, nitric, HNO3, and perchloric, HClO4. Okay? Those are the 6 strong acids. All the rest are considered weak. Now, what is the biggest difference from yesterday? What is the biggest difference in a strong acid and a weak acid? Right.
Weak acids have equilibrium and strong acids are just in one way. So
Exactly.
Weak acids dip the toe and strong acids do a cannonball.
Right. So a strong acid starts with HA and becomes A minus and H plus. Pretend that I curve. Anyway, so a strong acid, you start with HA. If you get a billion HAs, you get a billion H pluses and a billion A minuses. Anyone remember what this A minus is called? Yeah, it's called the acidic anion. Okay, so a strong acid disassociates completely into its acidic anions and hydrogens or hydroniums. A weak acid, however, has an equilibrium, and well, let me think. Would you draw the equilibrium like this, or would you draw it like this? So HA and H plus plus A minus. Would you draw the top equilibrium or the bottom equilibrium?
Bottom, because it's going over slow, but it's going back fast.
Is that? Can we agree? that right?
I don't know.
Okay, so basically this one would seem to indicate, this is not an official chemistry kind of thing, but it would seem to indicate that there was more acidic anions than molecules. This one would seem to indicate there's more molecules than acidic anions.
Yeah.
So who believes the top one's correct? Who believes the bottom one's correct? You're right, yeah. So when you have a weak acid, you have a lot more molecules than you have acidic anions and H pluses. And they are stoichiometrically related. It's a 1-to-1 relationship. Cool? All right. When we talk about bases, strong bases are easy to identify because they have hydroxide. Okay. Calcium hydroxide is a strong base. It doesn't dissolve very well, but it's still a strong base. Magnesium hydroxide is a strong base. Doesn't dissolve very well, but it's still a strong base. We're going to use a lot of sodium hydroxide. That's what we're using in the lab, hopefully tomorrow, maybe Tuesday, is a strong base. Anything that dumps hydroxide in solution is a strong base. Now, weak bases are things that make a solution basic by pulling a proton away from the water molecule. Okay? So K2CO3 is a classic example. When K2CO3 dissolves, it dissolves into 2 potassium ions, which we don't care about, and 2 carbonate ions. The carbonate ion is highly electronegative and will pull the proton away from water, forming HCO3 minus and OH minus. Okay. Does this kind of make sense, what I just explained really fast? So, strong base dumps the hydroxide. Weak base is something that has a very, very electronegative anion that pulls a proton from water, leaving a hydroxide behind, like the carbonate ion. Put the carbonate ion in, and you get this relationship. Okay, cool? Some of you are like, maybe I'll think about it. Cameron.
So when you ever see the it taking the proton in the chemical reaction, or would it be like one of the products would make it look like that? Did that make sense?
No.
So the first one.
Okay.
So the only reason why it takes the H plus, the reason that you know that is because of the one below it.
Right. Exactly.
Okay, so is it ever gonna look like the one below it in the above one?
No.
No. Okay,
No.
so it's gonna be like a molecule that does that
Yes.
as a product.
Is it going to be a molecule that breaks into a salt, or a salt that breaks into its ions, and it is the ion that will do that.
Okay.
So another classic weak base is ammonia. When NH3 is bubbled through water, it forms ammonium hydroxide, which is then in equilibrium with hydroxide and ammonia. So when this is ammonium molecule, when the ammonia molecule is in the presence of water, you get an equilibrium relationship where you get a molecule of ammonium hydroxide. Okay? Now there's a missing step in here, in that you actually make NH4OH, and then that's in equilibrium with the NH4 plus and the OH minus. So classic example of a weak base is ammonia. One we use a lot. Ammonia is a really fun molecule. Fun fact, so somebody mentioned about molecules, I think it was Brett talking about molecules that can be acidic or basic, in addition to water. Remember, if you put an acid you take some water, you put in an acid, the water is going to behave like a base. You take a base, put it in water, the water is going to behave as an acid. That's called amphoterism, where it can accept or give up a proton. Ammonia also does that too. Ammonia can actually accept a proton and form NH4, or it can give up a proton and form NH2 plus. Make sense? Or NH2 minus, Okay, shall we move on? Again, I don't expect us to spend a lot of time on this, but we should. Mastery is important to me. Concept mastery is important. So give me a thumbs up if you're ready to move on. Okay, put your hand up and wave around if you have questions. Okay, you can review it later, I guess. Okay, so there are 3 models to describe acids and bases. One is super general, one is useful, and one is really specific, and the College Board doesn't ask you to do it anymore. New for 2020. You don't have to do this one the last one anymore. Okay, the first one is called the Arrhenius model. And the Arrhenius model is super, super general, super broad, and basically says an acid is anything that shifts the water solution towards H+. Remember the balance of H+ and OH-. An Arrhenius acid is anything that shifts it towards H+. An Arrhenius base is anything that shifts it towards OH-. There's a million different mechanisms that'll do that. So very, very general, not super useful, but just realize that's the Arrhenius definition. Arrhenius has a formula that we're going to get to later on, but right now just realize that that's the Arrhenius model of an acid base. Super general. Acid is anything that shifts the balance of H+ and OH towards the H+. A base shifts it to the OH-. Okay. The definition that we use primarily, pretty much at all levels of chemistry, is the Bronsted-Lowry definition. The Bronsted-Lowry definition basically says, simply says, acids donate protons, bases accept protons. So it's all about moving the proton around. Acids donate protons, bases accept protons. That's the Bronsted-Lowry model. And it is the most useful and most relevant to what we're doing. Now, because this model is so simple, it leads to a concept called conjugate acid and bases. And what conjugate acid and bases are well, it's what a conjugate is what you get when an acid gives up its proton. A conjugate is what you get when a base accepts a proton. For instance, I have a proton. Capiche? So because I have a proton, I am an acid. Okay? And so I'm going to donate my proton to Brett, who's got his hands up, waving around. He's like, I'm a base, I'm a base. Give me a proton. Get the idea? So I'm going to donate the proton to Brett. Now, I have just lost my proton. So I would be classified as a base, but since since I just was once an acid, I'm not a normal base, I'm a conjugate base. Make sense? So an acid becomes a conjugate base. Now on the other hand, Brett was like, I'm a base, I'm a base. He just gained a proton, and by gaining the proton, he turned from a base to a what?
Acid.
A conjugate acid. Yeah. He turned from a base to a conjugate acid. Okay.
Doesn't conjugate mean like joined?
Yes.
That's what
It means paired up. Yep.
I should get conjugal visits in prison.
Yes, like conjugal visits in prison, right? So what we then create are what are called conjugate pairs, where an acid, its conjugate pair is the conjugate base, and a base, its conjugate pair is the conjugate acid. That's what conjugate means. Okay, questions? Give me a thumbs up if this idea makes sense to you. Okay, now we're gonna color it a little bit for AP. Remember this. A strong acid has a negligible conjugate base. Gesundheit. So think of a strong acid as infinity. So what is the opposite of infinity?
Negative.
Or like, sorry, the reciprocal of infinity. Zero. Okay? So a strong
Before answering
acid.
the question, in Super Bowl 53, the Patriots defeated the Rams 13-3
Alexa,
at
stop.
What was that?
I have no idea. That happens every now and then. Anyway, so
Oh, Super Bowl?
I have no idea what's going on there. Anyway, what it boils down to is a strong acid has a negligible conjugate base. So the conjugate base of HCl, so HCl is a strong acid, the conjugate base would be Cl minus. Cl minus is a negligible conjugate base, meaning technically it's a conjugate base, but it has no basic property. Does that make sense? Okay. Similarly, the conjugate of a strong base is a negligible conjugate acid. So strong base, good example of a strong base we're gonna use a lot is OH minus, and that's conjugate base acid is gonna be H plus, or sorry, Na plus. Their Na plus have no acidic properties at all. Cool? Now, that's for strongs. Question?
So if you mix a strong base with a strong acid, and they kind of, it's just not a super, the pairing up's negligible?
Yes.
Okay.
You will produce water and a salt, and we'll get to neutralization in a second. That's what the lab is going to center on, the idea of neutralization of an acid in the base.
So the NaOH is a strong acid? And then
Strong
it
base.
turns in- or a strong base? Okay.
Negligible acid, negligible conjugate acid. Strong acid, negligible conjugate base. Now, that's for strongs. For weaks, you probably figured it out, a stronger weak acid produces a weaker conjugate base. And a weaker weak acid makes a stronger conjugate base. Okay? If you have a pretty hefty, a pretty robust weak acid, like hydrofluoric acid, hydrofluoric acid's a pretty beefy weak acid, still weak, so its conjugate base, F plus, or sorry, F minus, would be a weak conjugate base. Okay? A strong, okay,
Is
weak
it
acids.
What's that word?
Negligible?
Negligible.
It's not negligible. It is considerable.
It's conjugate.
It's non-negligible? Sure, it's considerable. Anyway, so if you have a weak acid, a stronger weak acid makes a weaker weak conjugate base. A stronger strong acid makes a weaker weak conjugate base.
Okay, one more time. So stronger weak acid.
A stronger weak acid makes a weaker weak conjugate base. Strong, so we're talking about weak now, weak things. Stronger makes weaker. Weaker makes stronger.
Yes.
So a weaker weak conjugate, sorry, a weaker weak acid makes a stronger weak conjugate base. So talking about weaks, and again, this is the difference between AP and first year. First year, everything is acid base. Now it's strong acid, weak base, and stuff. So we were talking about weaks. A weaker something makes a stronger conjugate. A stronger something makes a weaker conjugate.
So like balance.
Yeah.
So if you use, what was the one time?
Hydrofluoric acid?
Hydrofluoric acid, you mix it with, what you say, ammonia, which is a weak base. Mix those, it make, since the weak acid is stronger than the weak base is strong.
We can't make that assumption yet. When we get to Ka and Kb values, then we can talk about stronger, weaker, weak, but we're not there yet.
So weak acid makes less a weaker strong acid. Strong
A stronger weak conjugate base.
Okay.
So a weaker weak acid
Yeah, okay.
makes a stronger weak conjugate base. Yeah.
Is there a way that I can make another acid?
Not sure what you mean.
Like how it goes from a strong weak acid to a weak base? Can I make the acid somehow? Like stay an acid?
A base, a weaker weak base, sorry, any weak base will make a conjugate acid. So a weak base will make a strong weak acid.
So I'll never be acid to acid, it's always conjugate.
Yes, it's always acid to base and base to acid. And you will never make a strong acid, you'll never make a strong base. Does that make sense? And a base cannot, no matter how weak it is, cannot make a strong acid. And an acid, no matter how weak it is, cannot make a strong base. One then two.
So it's never gonna end strong if you start with a strong acid?
Correct.
Okay.
This is only referring to when they like not a proton. The strong acid. An acid gives a proton to a base. That's what the.
Yes. An acid gives a proton to a species that becomes a conjugate base. Okay. I know, it's confusing. It'll get better, I promise. It'll get better. Okay, so if this makes sense to you, or at least you've accepted it, then give me a thumbs up. Okay. Now, the third definition, listen to it, remember it for 2 or 3 years from now when you go to college, but the College Board says you don't have to learn it anymore, and it is called the Lewis acid-base definition. Lewis acid base is based on electrons, not protons. Okay? So the Bronsted-Lowry is based on protons. Acids give up protons, bases accept protons. Lewis model is based on electrons. It's super specific, very useful for very specific circumstances. But because it's so specific, the College Board threw it out this year. Like, you don't have to learn this anymore. And it hasn't been on the Clark County curriculum for a decade. So just realize, Bronsted-Lowry an acid gives up pluses, and Lewis it accepts negatives.
Oh.
For a base,
It's just the-
it accepts positives, gives up negatives. Yeah, just the opposite. Again, it's used in a very specific circumstance where the proton is not available to move. So we don't care about that. Okay, so moving on. Anyone have any questions about this for posterity or trivia? Good, because we don't care. Okay. Alright, so we're talking about conjugate acid bases. Again, bases produce conjugate, acids produce conjugate bases, bases produce conjugate acids, and so on. So HNO3 this is wrong, this should not be in equilibrium, this should be a straight across arrow, but you know, what are you gonna do? So HNO3 is an acid, its conjugate is, you know, let's just forget it, you already know how to do this. How about this? See if you can identify the acid, the base, the conjugate acid, and the conjugate base.
Is this supposed to be equal?
Yes, yeah. Phosphoric acid is actually a weak acid. This should actually be in equilibrium.
Should we identify if it's gonna be a weak conjugate thing or a strong one?
That'd be a good idea.
Okay.
How do you know?
The thing that donates the proton is going to be the acid. The thing that accepts the proton will be the base. And the thing that previously donated the proton, in past tense, if you will, is going to be the conjugate base. And the thing that accepted the proton, in past tense, will be the conjugate acid.